G'day, Richard Marr here again from Mars Classes. Today we're going to have a look at conventional current and how it relates to electrical circuits and so forth. Now, a lot of people mistakenly say that Ben Franklin got it wrong when he was looking at conventional current because he said that it was the direction at which a positive charge will flow. I'm going to try and demonstrate that it's not entirely wrong. It's just the way it was defined, and we are now still following that same convention. So to look at this concept of conventional current, I'd like to again go back to looking at gravitational fields and how we define things in gravitational fields. Now remember, we said that when a mass in a gravitational field moves, when it spontaneously moves when the field does work on that mass, it'll spontaneously move in the direction that the field line indicates. So the mass in this instance is falling toward the Earth, and it has work done on it by the field. It's moved from a higher gravitational potential to a lower gravitational potential. In gravitational fields, masses can only really spontaneously move in one direction. It's not like an electric field where you have opposite charges, positive and negative charges, which can go in different directions. But when we do have an electric field, and we have a positive charge in an electric field around a negative charge, by convention we've said that the field line indicates the direction that a positive charge would spontaneously move when placed in an electric field. So that positive charge will move in that direction, but of course if we put a negative charge in that same field, it would move in the opposite direction. So what we've got in this instance is the positive charge has moved from a position of higher electrical potential to a position of lower electrical potential. Very similar to that elephant in the previous example, where it moved from a position of higher gravitational potential to a position of lower gravitational potential. Okay, now what does this mean in terms of currents? When we've got one charge moving, it's really just one charge moving. But when you've got multiple charges moving and they're all moving in the same direction, we can say there's an electrical current flowing. So I'm going to have a look at an example of a salt solution, a sodium chloride solution. Now when the sodium chloride dissociates in water, you have separated ions. I have oversimplified it because they are surrounded by water molecules and you have these spheres of hydration around them. But just very simply, I've taken the water molecules out and just looking at the sodium chloride ions throughout the solution, evenly distributed. Now if you place a couple of electrodes in there which aren't connected to an electric potential yet, and then you do connect it to an electric potential and complete the circuit, you'll find that the charges will all move and they'll migrate the negative charges to one electrode and the positive charges to another electrode. Now why has that occurred? It's because between the electrodes there is an electric field. And when we look at it, we can see that the positive charges have moved from a higher electrical potential to a lower electrical potential. That is, they've followed the field lines. But the negative charges have actually moved in the opposite direction. Now if we look at between the electrodes, we can see that there's a positive flow toward the right of the screen and a negative flow toward the left of the screen. That's between the electrodes, but on outside of the electrodes we actually had positive charges constantly moving to the negative electrode, and that can be from the right or the left of the electrode, and some from in front or behind the electrode are moving to it. So we can't really talk about one direction. All we can really say is that the positive charges have moved from a position of higher electrical potential to a position of lower electrical potential. Okay, now we don't have moving positive charges in a wire, a piece of metal, when it's in a circuit. So let's just have a look at what goes on there. If we had that same potential difference and stuck a wire in there, we'd find that spontaneously the negative electrons would flow from the lower electrical potential to the higher electrical potential. And the positive charges, while they are vibrating around their mean position, aren't drifting in one direction. However, despite all that, because the convention is when a current exists, that is a flow of charge exists, we define the direction of the current as being from higher electrical potential to lower electrical potential. And in the case of a piece of metal or a wire, it's going to be in the opposite direction to which the direction the electrons flow. If you want to talk about the current of the electrons, you would call it electron flow current or something like that. You'd actually specify that you're talking about electrons. But when we're talking about electrical current or conventional current, it is the direction a positive charge would move if it was moving. So I hope you understand that, because we're going to be using that in just about everything from now on. The convention is so strongly entrenched that we have hand rules, we have circuits which we draw, and we always represent the conventional current as going from the positive potential to the negative potential. Okay, look, there'll be a lot more on this. Just don't think that Ben Franklin got it wrong. He just was operating on the information he had at the time. They were unsure of what was actually the individual particles within the material which were moving, and they just had to decide on one convention, and the convention was that a current will flow from a positive electrical potential to a negative electrical potential, because it made sense when you looked at gravitational fields, when objects move from a high gravitational potential to a lower gravitational potential. Okay, I hope I haven't confused the issue, but more on that in subsequent videos. I'll see you next time.